All right, so let's talk about a more formal proof of L'Hopital's rule. And it uses an extension of the mean value theorem. So let's recall sort of the mean value theorem here. Remember, the mean value theorem had its start with Rawl's theorem. Rawl's theorem was if f is continuous on the closed bounded interval, differentiable on the inside, and f of b equals f of a, so we had the same altitude. Then what had to happen? Well, let's draw a picture. Let's see if the picture here I might remember the picture. So we're over the closed bounded interval AB. We have to start at the same altitude we end at, and the function is continuous and differentiable. So that means that continuous means I have to connect things with a connected line segment. Differentiable means there's no sharp turns. So it's got to do something like this. Do you remember what had to happen somewhere in between?
A point.
There's a point where the derivative had to be what?
0?
Yeah. So at some point in between A and B, you had to have the derivative zeroing out. In this case, we've got two of them here. But Rawl's theorem says there's at least one. And more generally, what's happening is, if you look at the slope of the secant line here, since f of a and f of b are the same, the slope of the secant line is 0. That's matching here the slope of the tangent line is 0. All right. So that was Rawl's theorem. And we proved it. We proved it using Fermat's theorem, which we had proved using definition of derivative. Then we had the mean value theorem, which on the surface looked a lot beefier than Rawl's theorem. And it said if f is continuous on the closed interval AB and f is differentiable on the open interval AB, and there was nothing about what's happening at the endpoints. So now the function could be at different places, A and B. So we maybe f of A is here and f of B is here. F is continuous and differentiable, so I have to connect the dots here with a smooth connected curve. So what had to happen is if I look at the slope of the secant line here, which I kind of missed, but oh well. That was f of b minus f of a over b minus a. Then at some point, that had to match the slope of the tangent line. So at some point, the tangent line and the secant line were parallel. So f prime of c would equal f of b minus f of a over b minus a. Okay? So to prove L'Hopital's rule, we need what looks like on the surface an even stronger version of the mean value theorem. But we'll use Rawl's theorem to prove it as well. And so really in the grand scheme of things, all of these things go back to Rawl's theorem. But let's take a look at this equation. So I think when we looked at the mean value theorem, it wasn't that long ago, but it's been summer, so it seems like a long time ago. I said you can kind of rearrange this a little bit. You can write this as f prime of c times b minus a equals f of b minus f of a. All right? And I said this is going to come in handy for us later on. Well, this is the first time it's going to come in handy for us. Because here's what I want to do, right? If you look at L'Hopital's rule, it involves two functions f and g. So to kind of motivate this extended mean value theorem, we want to show how there's actually two functions happening in this equation. So I'm going to look at the function g of x equals x. So if g of x equals x, then g of b is b, g of a is a, and g prime of anything is what? If g of x is x, what's the derivative at any point? So the derivative of x is always what?
Be f of g of b. Is that what you're looking for?
Nope, it's just 1. Derivative of g of x is 1. That's it. Right? So if g of x is x, the derivative is always 1. So I can look at this equation, and what I'm going to do is I'm going to write this as f prime of c. And instead of b, I'm going to write that sort of as g of b. A, I'm going to write that as g of a equals, and I'm going to write, well, this technically I could write as a 1. But this will be g prime of c, because that's 1, f of b minus f of a. So if I wanted to, I could rewrite this equation in this form. And this is essentially what the extended mean value theorem is that you can, if you have two functions f and g, you can always find a value c that makes this work. All right. So once again, on the surface, so the extended mean value theorem, it's also called Cauchy's mean value theorem, says this: if f and g are differentiable on some interval a, b, well, I say continuous, on the closed interval a, b, and if f and g are differentiable on the open interval a, b, then there is a value c between a and b, so that f prime of c times g of b minus g of a is equal to g prime of c times f of b minus f of a. And as long as the following things are, as long as g of b minus g of a and g prime of c are on 0, we can rearrange this and have f of b minus f of a over g of b minus g of a is f prime of c over g prime of c. And here you can kind of see the shades of L'Hopital happening. Okay. So let's prove this theorem. And we're going to prove it the same way we proved the mean value theorem. We're going to use Rawless theorem. We're going to start with the function, and we're going to show it satisfies the conditions of Rawless theorem. And then the c that we want is going to be from the conclusion of Rawless theorem. So we're going to do the same thing we did before. If we want two things in mathematics to be equal, then we want to show that their difference is 0. And the place where the c is, that's going to be where the x goes. So I'm going to rig up a function h of x to be f of x times the quantity g of b minus g of a minus g of x times the quantity f of b minus f of a. And what's important for you to remember, like back when we did the mean value theorem, what this is this is just f of x times some number minus g of x times some other number, okay? So we're just taking a multiple of f and subtracting a multiple of g. So the claim is Raleigh's theorem applies here. To h. All right, so let's see. Is h continuous? Sure. F and g are assumed to be continuous, and I've got a multiple of f minus a multiple of g. Combinations of continuous functions are continuous. Is h differentiable? So h is continuous on the interval ab. Is h differentiable? Sure. F and g are both differentiable, and I'm taking a multiple of f minus a multiple of g. In fact, I can take the derivative of h of x. What would that be? Well, you're taking the derivative with respect to x. And x only appears in these two places. So I can just do f prime of x times whatever constant that was multiplying it by. Minus g prime of x times whatever constant it was multiplying. We good taking the derivative there, folks? So derivative of f times a number minus derivative of g times a number. So now we have to show that h of a equals h of b. So I got to plug in x equals a. Once again, there's x is only in these two spots. So this is going to be f of a times g of b minus g of a minus g of a times f of b minus f of a. So you go through and distribute here. F of a, g of b minus f of a, g of a minus f of b, g of a plus f of a, g of a and we got some cancellation there. I'm left with f of a, g of b minus f of b, g of a. So that's h of a. So now I need to show h of b is going to work out to be the same thing. So let's look at h of b. Once again, x is only in two places, so I'm going to plug b in to those places. And I've got the f of b times g of b minus g of a minus g of b times f of b minus f of a so h of b equals f of b g of b minus f of b g of a minus f of b g of b plus f of a g of b and these two cancel out. So I've got f of a g of b minus f of b g of a. And hopefully that's the same thing I had before. And it is. So once again, if you go back and look at the proof of the mean value theorem, it was a very similar kind of thing, only there we had the function and we subtracted off its secant line. But it's the same kind of mechanic here. So by Rawl's theorem, there is a C and AB with h prime of C equal to 0. So I go back, because I have a formula for h prime of x. It's right here. And once again, the x only appears in these two places. So that means that f prime of C times g of b minus g of a minus g prime of C times f of b minus f of a equals 0. Or in other words, f prime of C times g of b minus g of a is g prime of C times f of b minus f of a. And that's our proof. So once again, in the grand scheme of things, we had Rawl's theorem, which gave us the mean value theorem, which gave us the extended mean value theorem. But the extended mean value theorem reduces down to Rawl's theorem. And so these are all logically equivalent. Okay. If you take g of x equals x, then the extreme value theorem gives you both of these. Okay. You kind of see how the proof goes together. Once again, this isn't something I'd ask you to come up with on your own, but you should be at the point now where you can follow the logic through. That's all I'm asking here. Just getting used to the nonsense. So how does that help us with L'Hopital's rule, right? Which is why we wanted to do this. Oh, let's before we do that, let's look at what the picture is. For the extended mean value theorem. We haven't studied parametrics yet in calculus. We will study parametrics in calculus in Calc 2. But you may recall from like pre-calculus trigonometry, you can sometimes describe a curve where each coordinate is a function of time. So I know we teach this in our trigonometry class here. And so you can think about a curve sort of being the path of like a bug that gets dropped out. then if you do it this way, the extended mean value theorem is saying the exact same thing that the mean value theorem is saying. Is that the slope of the secant line through the endpoints is going to be matched by the slope of the tangent line somewhere in between. Okay. But once again, this has to do with parametric. Parametric equations is the best way to visualize that. So there is a picture, and it's the same concept as the pictures we've had before. Okay. It's just easier to visualize with parametrics. So let's take a look at L'Hopital's rule. So we're going to assume f and g are differentiable at x equals a, and the limit as x approaches a of f of x over g of x is of the form 0 over 0, where g of x is not 0 in some open interval containing a. All right. Whoops. So last time we talked about why we knew that f of a and g of a were both 0. Look at that. Since, wow, I just don't get it. What is going on today? It's probably the humidity. I'm going to blame the humidity for that. So if f and g are differentiable at a, that means f and g are continuous at a. And since we're getting to the indeterminate form 0 over 0, f is going to 0, g is going to 0 as we get close to a, then that means f of a and g of a must be 0. Remember, continuity means you get what you expect. I'm expecting 0 out of both, so that's what I get. So what basically you do here is you apply the extended mean value theorem on the interval, well, a to x or x to a, depending on what direction you're coming from. And so what that says is that f of x over g of x, think of that as f of x then minus 0 over g of x minus 0, which would be f of x minus f of a over g of x minus g of a. And now we can hit things with the extended mean value theorem to say that this is going to be sum f prime of c over g prime of c. And so the limit as x approaches a of f of x over g of x would be the limit as x approaches a of f prime of c over g prime of c. But remember that the c here is between x and a. So as x gets close to a, c is also getting close to a. So I can just change everything back and put the x's back in. Oops. So that's going to be the same limit as f prime of x over g prime of x. Okay. So that's a more formal proof of L'Hopital's rule using the mean value theorem. Any chance we have to showcase the mean value theorem, I'm going to take it. Next week, the mean value theorem comes back big time to help us prove the fundamental theorem of calculus. Okay, so it's a big deal.